This is the first lesson in the 5th unit in the Calculus and Vectors course. This is the second vectors unit, and the unit is called Cartesian Vectors. And the first lesson is going to be an intro to Cartesian vectors. We're going to learn how to express vectors algebraically. So sometimes you'll hear Cartesian vectors, you'll hear them called algebraic vectors. We're going to learn how to define vectors algebraically using Cartesian coordinates. So in this lesson, you're going to learn about the two different ways we can express algebraic vectors, either as a position vector in component form, or you're also going to learn how you can express it as a sum or difference of unit vectors I and j. So make sure you've clicked the link in the description. You get a blank copy of the lesson so you can fill it out as we go along, and let's get started. So to start off this lesson, I just put a little blurb in here about René Descartes and how he was the first mathematician to actually figure out that we could kind of combine algebra and geometry by using a coordinate system. So feel free to pause the video here and read this whole thing, and then we're going to go ahead and actually start looking at how we can define vectors algebraically. So what are algebraic vectors? Suppose we have some vector u. So I have vector u over here. Let me just outline it in a different color so it's more obvious and it stands out for you. So I've got this vector u, which starts at some point q and finishes at some point p. Now, in order to define that vector algebraically, what we're actually going to do is we are going to translate that vector without changing its direction or magnitude so that its tail is at the origin. So notice how its direction, its magnitude has not been changed. But now that it's been translated so its tail is at the origin, now we can define this vector based solely on what is the point that its tip is at. So what are the coordinates of that point? And when we describe the vector in terms of that point, we use square brackets. That indicates that it's a vector and not just a point, right? It's a vector with its tail at the origin and tip at that point. So what it says here, it says if we translate vector u so its tail is at the origin and its head will be at some point AB, then we define that vector as position vector AB. So I think the coordinates of this point are 6, 8. So I could define this vector u, I could define it as a position vector 6, 8. I could say vector u equals 6, 8. And square brackets indicating that it is a vector with tail at the origin and tip at the point 6, 8. So when you're defining a vector, make sure you use square brackets. Alternatively, you could use triangular brackets like this. This is another notation that means the same thing. So when you see the square brackets or the triangular brackets, know that we have a vector that's tail is at the origin and its tip is at whatever the coordinates of that point are. So key takeaway here, when defining a vector, use square brackets. So use square brackets to distinguish between a point and a position vector. Part 2 looks at another way we can define Cartesian or algebraic vectors. It looks at how we can resolve them into unit vectors. And a reminder, a unit vector is a vector of magnitude 1. And there are two very common unit vectors that we work with when dealing with Cartesian vectors. We work with unit vector I, which can be denoted like this, I with a hat above it instead of a vector symbol. That's a common notation meaning unit vector I. And we know that unit vector I, it is commonly understood, is the position vector 1, 0, meaning its tail is right here at the origin and its tip is right here at the point 1, 0. So that is unit vector I. And it's commonly understood in vectors that that's what unit vector I is. And unit vector j, which could be written like this, j with a hat above it, is the unit vector 0, 1, which means tail at the origin, tip at the point 0, 1. So that's unit vector j. And why I'm telling you about those unit vectors is because we have a horizontal and a vertical vector, we know that we can resolve any vector into horizontal and vertical components. We learned about that in the last unit. So the rest of this is just explaining to you that we could define any vector as a sum of multiples of unit vector I and j. And let me just try and demonstrate that to you. So I have some vector that starts at the origin and finishes at point P, which has an x-coordinate of A and a y-coordinate of B. Now I could resolve that vector into a sum of its horizontal and vertical components. So its horizontal component would look like this, which is collinear with I, right? It's parallel to I, so I could express that as some multiple of unit vector I. Let's say A times unit vector I. And the vertical component I could express as some multiple of unit vector j, right? Unit vector j is perfectly vertical. So I could express the vertical component of this blue vector as some multiple b of unit vector j. And notice that this blue vector here, vector OP, is equal to this vector, a times unit vector I, plus this vector, b times unit vector j. So I'm just showing you that we can write any vector in terms of unit vector I and j. So that's all this is indicating that to you here. Any vector with tail at the origin, tip at some point, it's equal to a scalar multiple of unit vector I plus a scalar multiple of unit vector j, where the scalar multiple we use is actually equal to the x and y coordinate of where the tip of the vector is. So whatever the x coordinate of this point is, that's going to be the scalar multiple of unit vector I, and whatever the y coordinate of this point is, that's the scalar multiple of unit vector j. So when we actually do some examples of this, it's actually a lot more straightforward than that explanation probably was, but I hope you followed along. So this is just a summary of what we just talked about. So right now, this might not mean much to you. It means 2 space. We haven't even started working in 3 space yet, in 3 dimensions, but that'll be coming soon. So when representing vectors in 2 space, position vector, OP, can be represented either like this, where the square brackets indicate it's a vector, and A, B are the coordinates of where the tip of the vector is, understanding that the tail is at the origin. Or we could write it as a sum of multiples of unit vector I and j. And remember, it could be the hat symbols instead of the vector symbols to indicate that it's a unit vector, where the a and the b, the scalar multiples of unit vector I and j, are whatever the x and y coordinates of where the tip of the vector are. Example 1, we're going to practice representing vectors in 2 equivalent forms. So we're going to work at transitioning between position vectors and sums of unit vectors. So I've given you 4 position vectors. Let's rewrite each of those as sums or differences of unit vectors. And we're going to specifically write them as sums or differences of unit vector I and unit vector j. Remember, unit vector I is the horizontal vector with magnitude of 1, vector 1, 0. And unit vector j is the vector 0, 1. And those are shown in the diagram to you here. So I want to break up vector p into its horizontal and vertical components. Well, notice the horizontal component of vector OP is equal to unit vector I, and the vertical component is equal to 2 unit vector j's. Right? There's unit vector j, there's another unit vector j. So I could rewrite vector OP, as unit vector I plus 2 unit vector j's. What I want you to notice is that the scalar multiples of the unit vectors I and j are equal to the x and y coordinates of the point that the tip of the vector is at. Now let's try vector OQ. Since it's given to us as a position vector, we know that means tail is at the origin and tip is at the point -3, 0. So I can express it as a sum or difference of unit vectors I and j just by doing the x coordinate multiplied by unit vector I. So -3 times unit vector I plus the y coordinate times unit vector j. But there is no vertical component to this vector. So when I add 0 unit vector j, that doesn't affect it, so I can just write this as -3 unit vector I. Right? This vector is just equal to -3 times that vector. So now let's try vector OR. It's given to us as a position vector, so we know tip is at -4, -1, tail is at the origin. When I define this as a sum or difference of unit vectors I and j, I know that the horizontal component is going to be equal to the x coordinate of the tip times unit vector I, so -4 times unit vector I, plus the y coordinate of the tip of the vector times unit vector j, so plus -1 times unit vector j. So I could write this in a simpler version. Instead of plus -1 times vector j, I could just write minus vector j. And our last one is vector OS. Its tip is at the point 2, -1, tail at the origin, so it's the vector from here to here. I can write that as a sum of a scalar multiple of I plus a scalar multiple of j, and I can get those scalar multiples just by looking at the x and y coordinates. So vector OS is equal to 2 multiplied by unit vector I plus -1 multiplied by unit vector j. So I'll just write that as minus unit vector j. Let's move on to part B now, where we go the other way. So remember, the scalar multiples of unit vector I and j are equivalent to the x and y coordinates of the position vector. So vector OA, here we see it's negative unit vector I. I don't see a unit vector j, so there must be no vertical component to it, so I'll write it as +0 unit vector j. So as a position vector, I just take the coefficients of unit vector I and j, and those become the x and y coordinates of where the tip of the vector must be. So I can write it as vector -1, 0. How about vector OB? Here's vector OB. The coefficient of unit vector I is 1, and of unit vector j is 5. So this vector, written as a position vector, would be vector 1, 5. And vector OC, written as a position vector, just look at the coefficients, it would be -5, 2. Just make sure you have square brackets around each of these, indicating that it's a vector and not a point, right? These are the coordinates of where the tip of the vector is, and the tail of the vector is at the origin. Part 3, how about if we want to find magnitude of vectors? So now that we've defined vectors in terms of a coordinate system, we can find their magnitude using what we know about trigonometry. So if we look at this vector, so a position vector has its tail at the origin, tip at some point. If I want to figure out the magnitude of this, well, let's just break this into its horizontal and vertical components. So if I want the magnitude of it, remember Pythagorean theorem. Pythagorean theorem tells us that that side squared plus that side squared equals the hypotenuse squared. And what would be the length of this side? Well, keep in mind the coordinate of this point right here is 0, 0. And the coordinate of this point right here, I'm saying, is some x coordinate of vector v and some y coordinate of vector v. We'll define actual coordinates in a second when we do an example. But that notation just means the x coordinate of vector v and the y coordinate of vector v. So if I want the length of that side, I just have to find what's the difference in the x coordinates. So what's that x coordinate? -0. That's all this says here. So whatever the x coordinate of this is, that tells us the length of this side. And if I want the length of this vertical side here, I would just have to find the difference in the y coordinate. So I'd have to do that -0. Well, that's just that. And then from Pythagorean theorem, so let me label this. So this would have a magnitude of whatever the x component is. And this would have a magnitude of whatever the y component is. And then I could calculate the length of the hypotenuse, which is what we want. We want the length of that vector just by doing Pythagorean theorem. Pythagorean theorem would tell me that this side squared plus this side squared equals this side squared. And notice I put those absolute value symbols to indicate what we're finding is the magnitude of the vector. And then if I rearrange this, move the square to the other side, I get this formula. So this was all just a way of me showing you this comes from Pythagorean theorem. So if we have a position vector, we can find its magnitude just by doing the sum of the squares of the x and y components, and then square rooting it. That comes from Pythagorean theorem. So let's give that a shot. Let's find the magnitude of this vector. Find the magnitude of vector 7, 4. And when it's written like this, you have to understand by now that means that the tail is at the origin, the tip is at 0.74. So if we want the magnitude of this vector, well, look, what's the horizontal length here? What's the length of this side? Since this is 0.74, this length must be 7, and this length must be 4. So just do Pythagorean theorem. The magnitude of vector v squared equals 7 squared plus 4 squared. So the magnitude of vector v equals the square root of 7 squared plus 4 squared. And then we can get an exact value for this. 49 plus 16 is 65, so we get root 65. So that's an exact value for the magnitude of that vector. So you don't need to show this line. We can go right to this line. This is the formula we generated. Just make sure you know that it comes from Pythagorean theorem, where what goes here is the x component of the vector, and what goes here is the y component of the vector. Part 4, adding and subtracting vectors. So now that we're working with the Cartesian coordinate system, adding and subtracting vectors is actually really nice. We no longer have to take out our rulers and measure and reposition vectors and do all that stuff. We can just use the coordinates and algebraically define what the sums and differences of vectors are. And the formula for adding vectors is actually really straightforward. To get the x component of the position vector, you just add the x coordinates of vector b and u. And to get the y component of the position vector, you just add the y coordinates of the vectors. And that gives you the position vector v plus u. So make sure you understand in this notation, v subscript x, that means the x coordinate, or the x component of vector v, and u subscript x means the x component of vector u. So when we have two vectors, let's actually do work with some actual vectors here. Vector v equals position vector 7, 4, and vector u equals position vector 2, 6. Let's figure out what vector v plus u looks like. So I have drawn for you here vector v and vector u. And remember, when adding vectors, let's think geometrically. When adding vectors, what we have to do is actually reposition them so they're tip to tail. Now, we're not always going to have to do this. This is just to make a connection back to last unit. So when we connect them tip to tail, like we take vector u, we keep its direction and its magnitude, and we move it so it's tip to tail with vector v. And then the sum of those vectors goes from the tail where we started to the tip of where we finished. So I've got that mapped off for you. So vector v plus u equals, I just need to add the x components, so 7 plus 2, comma, add the y components, 4 plus 6. And that will give me the position vector v plus u. So I get vector 9, 10. Right. Vector u had a horizontal component magnitude 2. Vector v had a horizontal component magnitude 7. So u plus v, its horizontal component, is the sum of those two. It's now a horizontal component of 9. And same with the y components. Just add the vertical components, add the vertical component of v plus the vertical component of u, and we get the vertical component of u plus v. So basically just add the x components and add the y components. How about subtracting? Subtracting, same thing. Just subtract the x components and subtract the y components, and then we get the difference vector. So there's a diagram here to help you understand that as well. But maybe I've over-explained up to this point. So let's just go ahead and use the formula, right? It's the same as the addition formula, but subtracting. So if we want to calculate vector v minus vector u, I can write it as a position vector, where I'd find the difference of the x component of vector v with the x component of vector u, so 7 minus 2. And then to get the y component, I do the y component of vector v minus the y component of vector u, so 4 minus 6. And what I get for vector v minus u is vector 5, negative 2. So that's a vector with its tail at the origin and its tip at the point 5, negative 2. Notice 5, negative 2. So we found the vector algebraically. Let's move on to multiplying vectors by a scalar. So if we want to multiply vector b by some scalar k, all we have to do is multiply the x and the y components of that vector by that scalar k. So if vector v is vector 7, 4, right, the position vector 7, 4, tail at the origin, tip at the point 7, 4, let's find 2 times vector v. Well, remember, 2 times vector v is in the exact same direction as v, but double the magnitude. So that means its x component is going to be doubled and its y component is going to be doubled. So let me give you a visual demonstration of this. So notice here I have 2 vector v, right? Vector v plus vector v, that's 2 vector v. Well, what's the x component of one of those vector v's? It's right there. What's the x component of 2 times vector v? Well, it would just be 2 of those. It would be double it. Right? There's the x component of 2 vector v. And same logic for the y component. So if I want to actually calculate, right, the length of this line was 7, and the length of this line was 7. So the new horizontal component of 2v is going to be 2 times 7, 14. And same logic with the vertical component. So when I calculate 2 times vector v, 2 times vector v, I just have to do 2 multiplied by the position vector 7, 4. And based on the formula up here, that tells me that all I have to do is distribute that 2 to the x and the y component. So this equals 2 times 7, as the x component and 2 times 4 as the y component. So 2 times vector b written as an algebraic vector is 14, 8. And notice the coordinates at this point would be 14 and then 4 plus 4, 8. So this would be 14, 8 is where the tip of the vector is. So I put a little recall in here before we do example 6. Just note that if two vectors are collinear, they can be drawn so that they're on top of the same line. And the only way that can happen is if those vectors are scalar multiples of each other. So u and v are collinear if u is equal to some scalar multiple of v, right? A scalar multiple, all it does is it affects its magnitude and could possibly change it to the opposite direction, but they would still be collinear. So if vectors are collinear, they're scalar multiples of each other. So how do we check if they're scalars of multiples of each other? So what we can do is we can just check, is there some scale factor that keeps the ratio from the x components the same as the ratio to the y components? So example 6 wants us to check if u and v are collinear. So the only way they could be collinear is if vector u was equal to some scalar multiple of vector v. So that would mean that 3, 5 over 6 was equal to k times vector v, negative 3 over 2, negative 5 over 12. So how can we check if this is true? Well, remember, when you do a scalar multiple of a vector, the x and y components get multiplied by that scalar. So 3, 5 over 6 must be equal to negative 3 over 2 times k, negative 5 over 12 times k. And now we need to check, is there some value of k that makes this true? Is there some scale factor that keeps the ratio between the x's and the y's the same? So in order for this to be true, in order for this vector to be equal to this vector, the x components have to be equal. So 3 must be equal to negative 3 over 2k. And the y components must be equal. 5 over 6 equals negative 5 over 12k. And now we just have to solve both of these equations for k. So we have to figure out, is there a single value for k which makes this true, which keeps the ratios of the x and y components equivalent? So solve each of these equations for k and see if we get the same answer. So we have 3 equals, let me just write that k in the numerator, multiply the 2 over, and then divide the negative 3. I get k equals negative 2. So the ratio of the x components, the scale factor is negative 2. How about for the y components? So I have 5 over 6 equals negative 5k over 12. Let's cross multiply. I get 60 equals negative 30k. K equals negative 2. So it's the same scale factor. So these are scalar multiples of each other. So what I could say is vector u, so my final answer, vector u equals negative 2 vector v. They're scalar multiples of each other. I found a single value for k. So I know they're scalar multiples, which means they must be collinear. Therefore, collinear. All I would have to do is multiply vector b by negative 2, right? Multiply that component by negative 2 and that component by negative 2, and I get vector u. So therefore, they're collinear. Part 6, Cartesian vectors between 2 points. So what if we were just told where the vector starts and ends, but its starting point is not at the origin? How do we translate that vector so we can describe it as a position vector? And what I mean by that is, how do we take that vector without changing its magnitude or direction and move it so that its tail is at the origin? And by doing that, how do we figure out what are the coordinates of where the tip is? So if I take that vector between point 1 and point 2 and move it so its tail is at the origin, how do I figure out how to describe this as a position vector? How do I figure out what the coordinates of that point are? So we can calculate that. The formula is actually not that difficult at all. All we have to do is find the difference in the x coordinates to get the x component of the position vector, and then find the difference of the y components to get the y component of the position vector. And the one thing that's important here is to note that point 1 is the tail, and point 2 is where the tip of the vector is. So the order that we do the subtraction is very important. So notice that point 2 is the tip and point 1 is the tail. So when we find the difference in the x components, we always do the x component of the tip minus the x component of the tail, and the y component of the tip minus the y component of the tail. And if we do that, what we'll figure out are the coordinates of that point, so then we can describe it as a position vector. So let's go ahead and practice that. if we want to figure out how to describe vector AB as a position vector, and all we're told is that vector AB starts at this point, right? Because in this notation, whatever letter comes first, that's the tail of the vector, and whatever letter comes second, that's the tip of the vector. And we know the coordinates of the tail and the tip, right? This is the tail, and this is the tip. So if I want to describe this vector that goes from here to here, from point A to point B as a position vector, I have to figure out, if I were to take that vector and move it so its tail is at the origin, what are the coordinates of the point at the tip? And to calculate that, we'll just use this formula right here. To get the x component, do x tip minus x tail. To get the y component, do y tip minus y tail. So vector AB is equal to get the x component, do x tip minus x tail, so 7 minus 1. And to get the y component, do y tip minus y tail, 2 minus 3. So vector AB is equal to 6, negative 1, right? The coordinates of that point right there, 6, negative 1. But now we know how to do it algebraically. We don't need to reference a graph to figure it out. And let's notice the question also asks us to find the magnitude of the vector. Right, when finding the magnitude of the vector, all we're really doing is Pythagorean theorem. We know that that length is 6 and that length is 1. Pythagorean theorem, we could find that side. And what happens is when we use the formula for the magnitude of position vector, the magnitude of vector AB is just equal to the square root of 6 squared plus negative 1 squared. We just put the x component of the position vector there, the y component there. And this formula just comes from Pythagorean theorem. And then if we evaluate this, 36 plus 1 is 37, so the magnitude of vector AB in exact form is root 37. And those absolute value symbols mean magnitude of. Let's do 2 more examples of this. So vector CD. I'm told the coordinates of where the tail is and the coordinates of where the tip is, so let's write it as a position vector indicated with the square brackets by doing the x coordinate of the tip minus the x coordinate of the tail. That will give me the x component of the position vector. And now do y tip minus y tail. That will give me the y component of the position vector. And I get position vector 10, 10. What's the magnitude of that? So the magnitude of vector CD would equal the square root of the sum of the squares of the x and y components. So 100 plus 100 is 200. So the magnitude of vector CD equals the square root of 200, which could be simplified to 10 root 2. Right? That would split into root 100 times root 2, so that's 10 root 2. Part C, vector EF. Once again, let's write it as a position vector. So to get the x component, I do x tip minus x tail, so 1 minus 4. And the y component, the y value of the tip minus the y value of the tail, so negative 7 minus negative 3. And vector EF is equal to negative 3. And then negative 7 plus 3 is negative 4. And then its magnitude, using Pythagorean theorem, I figure out it's equal to the square root of negative 3 squared plus negative 4 squared. So 9 plus 16 is 25. Square root of 25 is 5. So the magnitude of vector EF is 5. Last section of this lesson. Let's look at how, if we're given information about a geometric vector, how we could rewrite it as a Cartesian vector and then make the math with them actually quite a bit easier. Let's see what I mean. So to write a geometric vector in Cartesian form, so as an algebraic vector, we'll use trigonometry. So in the previous unit, we found that the magnitude of the horizontal component is equal to the magnitude of the vector times cos theta, and the magnitude of the vertical component is equal to the magnitude of the vector times sine theta. And from this diagram, we can see that if we have vector v here, notice that the horizontal component of it, if I were to do cosine from theta, cos of theta would equal the adjacent side, the horizontal component, divided by the hypotenuse, so the magnitude of the hypotenuse. Rearrange this, multiply magnitude of vector v over, and we figure out that the adjacent side is equal to magnitude of v cos theta. That's where this comes from. And then same reasoning for how we figure out that this vertical component is equal to the magnitude of v times sine theta. So we figured out that last unit in the last lesson where we learned how to write vectors in terms of a sum of its horizontal and vertical components. And another thing to note here is that theta is the angle the vector makes with the positive x-axis. So we call that the principal angle. So if we know the horizontal and vertical components of a vector, then we can write it as a position vector because we know the x and y coordinate of where the tip of it would be if the tail was at the origin. Right? I could write this point as magnitude of v cos theta, comma, magnitude of v sine theta. And then therefore I could write it as a position vector v equals magnitude of v cos theta, comma, magnitude of v sine theta. So that's a geometric vector written as a Cartesian vector, an algebraic vector. So let's try that for example 8. Write a force of 200 newtons at 20 degrees to the horizontal in Cartesian form. So a force of 200 newtons at 20 degrees to the horizontal. Let me just draw a quick diagram of that for you. There we go. So I have that drawn for you. So if I want to write this as a Cartesian vector, I just need to figure out, well, what are the coordinates of that point? Oh, and I should label the angle here and the magnitude. So this is 200 newtons and 20 degrees to the horizontal. So if I want to figure out the coordinates of that point, well, this side would just be equal to 200 cos 20. And this side would just be equal to 200 sine of 20. And that's from the formulas that we talked about over here. And so if I want the coordinates of this point, I know that this vector, so I'll call this force vector, I'll call it vector F, is equal to, as a position vector, 200 cos 20, comma, 200 sine 20. And then I could get approximate values for these x and y components if I wanted to by evaluating them on my calculator, making sure that you're in degree mode. Let's try example 9. Last example. A ship's course is set to travel 23 kilometers an hour relative to the water on a heading of 40 degrees. That means from north, clockwise, the angle is 40 degrees. A current of 8 kilometers an hour is flowing from a bearing of 160. So if this angle is 160, I could break up that 160 into that 90 degrees and this 70 degrees, which means this here is 20 degrees. And to describe it as an algebraic vector, I need to reposition it so its tail is at the origin. So let me just redraw it so it's here. And then knowing that opposite angles are equal, I would know that this angle in here is 20 degrees, which means that this full angle, 90 plus 20, I'll call that theta, is equal to 110 degrees, right? Because when I write it as a Cartesian vector, I always need to know the angle between positive x-axis and that terminal arm, that vector. So I can now describe each of these vectors algebraically. Oh, I forgot to label the magnitude of this vector. This vector, its magnitude was 23 kilometers an hour. And the magnitude of this vector was 8 kilometers an hour. So this vector is about the ship's speed, so I will call this vector S. Its x component is equal to the magnitude times cosine of the angle, and the angle from the x-axis, so that would be 50 degrees, so cos 50. And the y component is the magnitude of the vector times sine of the angle from positive x-axis to the vector, so sine 50. Now let's do the vector that's the velocity of the water. So I have it so its tail is at the origin, that's important. I have the angle between x-axis and that vector counterclockwise, that's also important. Now I'll call this vector W. The x component equals the magnitude of the vector, 8 times cosine of that principal angle, 110. And the y component would equal its magnitude times sine of the principal angle. Part B wants us to find the resultant velocity of the ship. Well, remember the resultant velocity is going to be equal to the velocity of the ship plus the velocity of the water. And now that we know how to add vectors algebraically, we don't have to worry about drawing a diagram and measuring and using trigonometry to figure it out. We can actually just add the x and the y components of these two vectors, right? If we want to get the resultant, and the result, I'll just do part B here. if I want to get the resultant vector, I'm just going to have to add the ship's velocity plus the water's velocity. And since I have those defined as algebraic vectors, I just have to add this vector and this vector. So add the x components. So 23 cos 50 plus 8 cos 110. And to get the y component, I'll just have to add the y components of those two vectors. So 23 sine 50 plus 8 sine 110. So this is an exact answer for what the position vector of the resultant is, but it would be helpful in this scenario to maybe evaluate this approximately. So we could just type those x and y components on the calculator and get an approximate answer, and I'll just give that to you. And now that I have the approximate values for the x and y components, I can find the magnitude of the resultant just by using my magnitude formula, Pythagorean theorem. So doing the square root of the x component squared plus the y component squared. And if I evaluate this, I'll get an approximate answer. It's about 28.785. And the units we're in are kilometers an hour. We should also describe the direction of this resultant vector. I mean, this does describe its direction, but let's describe the direction as an angle. So let me just draw a little diagram of what this resultant vector looks like, right? So it's not going to be perfect, but I know the x component is 12.048 and the y component is 25.137. So if I were to draw that resultant vector, its tail is going to be at the origin and the tip is going to be at that point, 1225-ish with those decimals. So that's what the resultant vector looks like. If I want to describe the direction of this vector, we probably want to figure out this angle in here. And if I want that angle, it would be useful to know these two sides of the triangle. Well, this would be equal to the x component, so 12.048, and this would be equal to the y component, 25.137. And then I could just use an inverse tan ratio to calculate that angle. Inverse tan of opposite 12.048 over adjacent 25.137, and then I can get that angle. And that angle is about 25.6 degrees. And so my final answer, I could say the resultant velocity of the ship is 28.785 kilometers an hour at a bearing of 25.6 degrees. All right, that's the end of the first lesson. So we covered a lot of new formulas and a lot of new concepts. Make sure you follow the link in the description, get the practice questions, and try them out.